Hello everyone, welcome back to our tutorial 4 as part of our image analysis essentials using Python series. And if you haven't watched the first 3, I seriously recommend you to do that first. And in the last one, we did talk about decision trees and random forest, and we achieved about, I forgot, 64% or so of accuracy using the handcrafted features. And we're going to do pretty much similar here. We are going to use exactly the same handcrafted features and use a multi-layer perceptron as or a neural network, let's say, as a classifier and see if we get any better accuracy or if we are limited by the handcrafted features that we are actually generating. Now, the core part of this tutorial is not just getting the best accuracy. This is not that type of tutorial series. This is more about educational series, which means you'll learn about how a single neuron actually works, what a multi-layer perceptron is, and what actually happens when you're training a neural network, and what certain parameters mean as part of the neural network. So if that's of your interest, again, there is a lot of content out there. My focus is on image analysis, and in the context of image analysis, how this actually fits in. Okay, now let's go ahead and jump into our Google Colab and continue our discussion over there. I've added a lot of description as part of the Colab notebook, so please download that and learn at your own pace. Okay, let's jump in. And this is the same notebook that we have used in the last 3 tutorials, so this is just a continuation. We stopped right there in our earlier tutorials and now let's go ahead and continue with tutorial number 4, which is neural networks from scratch. And I hope, let me go ahead and zoom in one step so you can read this even if you're watching on a small screen. And let me not waste your time by going through the series overview. We know we are in this single neuron, and then the next one would be convolutional neural network. That's all I can say. Let's go ahead and run this setup. I mean, I have actually did execute every cell here, so we don't waste our time. Multi-layer perceptrons, again, in this case, we are using some artificial neural networks, but I still left my runtime to CPU. We'll switch that to GPU in the next tutorial when we do convolutional neural networks, but for the handful of, when I say handful, a few thousands of these neurons, CPU is okay. I try not to consume GPU even though it's free, because maybe someone else is waiting for this same GPU, so we need to be mindful. Okay, all these libraries, we have used them, imported them in the last tutorial, pretty much the same thing, including the standard scaler to actually scale the values. For example, once you extract your features, the values can range from, 0 to 100 in one feature, or 0 to 0.1 in another feature. We need to bring all of those into similar scale, and that's why we use standard scaler. Train, test, split. Well, you have your data and you want to split that into 80% training, 20% testing. This can be very useful in doing that. And now we are actually importing TensorFlow. You can do, Torch if you want, PyTorch, but I'm using TensorFlow because it makes learning easy, especially the Keras interface of TensorFlow. Layer is a single layer of neurons, for example, that you're actually adding to your neural network model. We'll talk about these as we get in. Early stopping. Again, when you're training a model, you don't want to train until all the epochs are done if the model is not learning, so why not just stop early? And that's what we use it for. And reduce this on plateau is, in fact, as the name says, reduce learning rate on plateau. So if the learning rate, again, you schedule the learning rate, so you decrease the learning rate or increase the learning rate, let's say, accordingly. I don't know why I'm explaining all of this without getting in. We will talk about this once we get there. Okay. Not much to describe there, and we have already downloaded the dogs versus cats dataset. Feel free to download it yourself. And if you manually download it, please, if you want this code to work right out of the box, please place them in a train directory under cats and under dogs. All the cats images are in cats, all the dogs images. You can change these cats and dogs to malarial infected cells versus healthy cells. It doesn't matter. This is a binary distribution. As long as you have appropriately labeled these two and then dumped all your images, it should work. And this part of the code, we download the dataset if we haven't already done so, but we have downloaded it, so we shouldn't worry about it. And this function here, load RGB, obviously, as the name suggests, it's going to load the RGB image, and we are using OpenCV to load the image, which means it loads the image as blue, green, red channels. Again, watch my first video, I guess, where I talked about it. And we are converting that to RGB, red, green, and blue, which is the typical convention. That's the load RGB. Apply Gabor is another function. So Gabor filter, I talked about it in the last tutorial. It is a function of frequency, theta, and a whole bunch of other parameters. And when we call this function, we are going to extract features using Gabor accordingly. Now, talking about extract features, that's the next step. All it's doing is load this RGB image, whatever the color image that we have. It stores that image, and then it also converts it into grayscale, and it stores it in another variable called gray. We are converting that to gray. And then from each image, we are just getting statistics, like we're getting the mean, standard deviation, the 10th percentile, 90th percentile, and we are also getting other features like blurring the image using Gaussian blur, and then we get the blurred mean, blurred standard deviation, and a whole bunch of other features, okay, including the Gabor features right there, for various theta and for various frequencies. So we get like a whole bunch of these features, I believe like 65 to 67, we'll see. And that's our feature vector. So each image has a feature vector, and that feature vector goes into whatever the classification model. It can be random forest, it can be neural network, and whatever the model that you're using, it goes through that. Now, how many images are we using for training? In this case, we are using 1128 cats, 1128 dogs. Okay, for each class we have that many images, and from each of those images we are extracting the features. And once the features are extracted, I already mentioned the features, depending on what feature you're extracting, the range of these values vary. That's why we need standard scaler to actually standardize and scale them to a specific range. So X scaled is where you have all the feature vectors ready for training. Well, once it's ready, we split that into training and testing data set. In this case, we are doing 75% for training, 25% for testing. That's it. So this entire cell, I hope, makes sense. Now, this takes a little bit of time, so I have done it right literally a few minutes before I started the recording. Okay, so now that we have the features, now let's go ahead and train a neural network. But you need to understand what neural network is, what a neuron is, and what is this entire story about, how does it actually work. Well, if you understand the biological neuron, I'm not sure if I should zoom out, but this is good. A biological neuron, you have the cell body, and what is this central thing? That's a nucleus. So you have a cell body, and you have dendrites. These things, they're all dendrites sticking out, and they connect to another neuron and so on, right? So you have the dendrites that carry the information to the cell body. So each dendrite, let's say, is bringing in some information to the cell body, and the cell body decides what to do with that information and sends an output to the axon. This is how our actual biological neurons work. And the axon carries that information to the next level. That's it. Now, real artificial neurons work pretty much the same way because they're modeled after this. It receives several input values, x1, x2, x3, x4. So each of this, x1, x2, x3, x4, x5, each of this is bringing in some input. That's what that is, x1, x2, x3. And then each information, so each of this information has some weight to it. Maybe the information coming from this is not highly weighted, and information coming from this other dendrite has more weight to it. That's what we mean by weights right here. So you multiply x1 with its corresponding weight, w1, and when you do that, when you multiply these, add all of them, and then add another term called bias. It's right here. That's what you define as the output that's coming out from your axon. So inputs coming from dendrites, each input has a value and also a weight that we multiply with the value. And then all of those go into cell body, and the cell body is nothing but a mathematical formula of x1 times w1 plus x2 times w2 plus x3 times w3, so on, how many ever neurons you have. All of that plus another term called B, which is a bias term. That's it. That's your output. You may be thinking this is no different than linear equation. This is literally a linear equation. AX, plus BY, or AX1 plus BY1 plus, BX2 plus CX3, whatever. This is the linear equation plus a constant, right? So, but people say neural networks are nonlinear. They have to be nonlinear, otherwise just use linear regression. And where does that nonlinearity comes in? Well, first of all, it comes from the activation function, which we'll discuss in a minute. But without this activation function, if you just use the pure linear equation like the one I showed up here, then stacking multiple layers of neurons, that's nothing but a single layer. You can stack any number of these neurons. It doesn't matter. You have layer 1, layer 2, layer 3. It's like a single layer. It's like a single linear equation, basically. No matter how many linear layers you stack, the result is still a linear transformation of the input. So you get the input, you're linearly transforming it to some sort of an output. Okay? So that's like a linear regression, but you need non-linearity because the real classification is you can never draw a straight line and separate cats versus dogs. We saw that earlier in random forest. You have to have some sort of a curved surface that separates the data points or features in n-dimensional space between cats versus dogs. I hope that makes sense. And activation functions introduce that nonlinearity that's needed to do that learning. Okay, so let's visualize the 4 most common activation functions. This is a fast execution, so it doesn't matter. I accidentally hit the run. It should be pretty fast. And the main activation functions that get used in neural networks are the sigmoid function. And you probably know what a sigmoid function is. It looks like an S curve, right? I think that's what we're doing. We're plotting. Tanh, ReLU, rectified linear unit. That's what that stands for. And leaky ReLU. Okay, leaky rectified linear unit. You'll see what that is in a minute. So all we are doing is taking some input. We are generating numbers between -5 to 5, 400 of them, and we are applying these different functions to it. That's it. So we can visualize it, and we are plotting them down here so we can visualize these functions. So these are the common activation functions, sigmoid. What in the world does it even mean? What am I talking about? Activation functions. Well, let's take a step back here. We do this math. I hope this makes sense. So you have a neuron and you have a value of x1 and a weight of w1. x1 plus w1, x2 plus w2, blah, 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 whatever, and plus b, you get some output. That output value, now hold it right there. That output value, if that is, -2, then when you multiply with the sigmoid function, that -2 becomes 0.1 about right there. So on the x-axis here, you have the raw value before applying any activation. On y-axis is the actual value after applying the activation. So for sigmoid function, you see if the output value from our neuron is 0, then it's 50, 0.5 for sigmoid. Okay. Now, if you let's focus on 2 numbers. Let's say -2 and +2. If the output from our calculation. -2, you get a probability of or a value of 0.1. +2, you get a value of 0.9 if you use sigmoid. Now, if you use the Tanh, -2, it's a value of almost like -0.9 or something. And if it's +2, it's about 0.9. If you consider the y-axis as the probability, then you're actually getting 0.9 right here, okay, 90% or something. Now, ReLU, rectified linear unit, is almost all the time, most common one that gets used in neural networks for a good reason, because if the value is below 0, if the value from our calculation is below 0, then the output is 0. If not, then the output is whatever the output is. This is linear. Yeah? So that's rectified linear unit. So below 0, the value drops to 0. And above 0, it's just linear unit. It's in simple terms, take the value. If it's negative, then just drop to 0. If it's positive, just take the value as is. Okay, that's what rectified linear unit is. And leaky ReLU is very similar to that, except below 0, it doesn't drop to 0. It just slowly goes down. Okay, that's only difference. Now, ReLU is the workhorse of deep learning that gets used almost all the time. And again, I mentioned it's the max 0z. What basically means is it's either 0 if the value is less than 0, or it's equal to z if the value is equal to is above 0. That's what this is. And already mentioned all of these. The main weakness of ReLU is something called dying ReLU. So if a neuron's pre-activation value is always negative for all the training samples, right? I mean, if you look at this, if the output that's coming from the neuron is less than 0, we are saying drop all the values to 0. If it's not, then take the value, whatever the actual value is. But what if every neuron is actually giving you a negative value and you're dropping everything to 0? Model will never learn anything because your output is always negative, right? So that's exactly where leaky ReLU can actually help. It allows a small negative slope, so you actually have some values to work with. That's basically the reason why you have that. So let's actually look at now that you understand how a neuron actually works, right? A artificial neuron. This is which is based on the real neuron. You know how it works, and now you know how this activation works. Let's actually visualize it in a real example right here. So this is a artificial neuron that kind of looks like real neuron, except it only have two dendrites. Dendrite number 1, x1, dendrite number 2, x2. Remember the features that we just extracted? Let's actually map it to those features. In fact, these are real numbers that we are using from those features. Let's say the Sobel mean. One of the features is Sobel mean. One of the features is the red cherry mean, which is the specific channel in our image. Our image has multiple channels, let's say. And you have this mean. And in one case, the value is minus 0.928 and here 0.663. Okay, these are just x1 and x2. They're connected to our cell body through something that has a weight of 0.6 for the x1 and minus 0.4 for x2. So all this is doing is just computation. Minus 0.928 multiplied by 0.663 times minus 0.4, and then add them together and also add this bias 0.1. When you do that, you get a value of 0.722 right here. In fact, did we do the math? Yeah. So when you do this and when you add all of this, you get minus 0.7224 actually. Yeah. So that's what the sum that you have. Now, it goes through a ReLU. Okay. And in this case, the value is minus 0.722, which means this one, it's converting or minus 0.722 to 0. So your output is 0. If this value were 0.722, the positive side, then the output would be 0.722. Because it's negative, it's dropping our value to 0. I hope this makes sense. And this value gets fed into the next neuron that's connected to this neuron. Okay, and this is where the nonlinearity comes. Otherwise, this is a linear equation. Okay, now we understand one neuron. Let's now put a bunch of neurons together. And when you do that, it's called a multi-layer perceptron. So neurons are organized into layers in a fully connected dense network. Every neuron is in one layer is connected to every neuron in the next layer. So if I go here, You can see x1, x2, x3, x4, blah, 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 how many ever x's you have here. This is, in our case, this is, if we say our feature vector has 67 values, and this is x1 all the way to x67. These are the values of our features. And in the next layer, you may only have 64 neurons, not 67, but 64 neurons. So each and one of these 67 neurons are connected to the 64 neurons in the next layer. So this is called fully connected. And the next layer may only have 32, and the next layer may only have like a subset of them. And finally, we have one value, that's it. That's the output layer in our example, because we're working with a binary classification scenario. Well, you may ask, if it's binary classification, shouldn't we have two of those? One for cat, one for dog. No, if the value is 0, it's cat. If the value is 1, it's dog. If the value is 0.3, it's more probable that it's a cat. If the value is 0.8, it's more probable that it's a dog. So the values go from 0 to 1. You only need one single neuron. If it's a 3-class classification, yeah, I agree. You need 3 different neurons, one for each output. Yeah, so please don't be confused here. But the whole point here is, we previously looked at single neuron, or sorry, 2 input neurons, x1, x2, and then they're connected to, one cell body, and then you get that output, right? So that's all wrapped in here, and you have your weight right here, and each of this is connected to each of the other ones. This is called a multi-layer perceptron, and these are the ones in the middle are called hidden layers. And the deeper it goes, the more, this is where the term deep learning actually comes into picture. The more layers and the more deep, or the deeper the network actually is. And you need to be careful. If the network is too deep, you may be actually learning a lot about the training data, but not generalizing it. We'll get to that in a minute. So input layer, 1 node per feature. Again, we have 67 features in our feature vector, so you have 67 nodes in the input layer in our specific example. And nothing happens, right? No computation happens here. It just holds the feature values. And this gets connected to the hidden layer. So each neuron computes a weighted sum of all inputs, right? So we know this weight 1, weight 2, weight 3. So x1 times w1, x2 times w2, and all that. And it adds a bias and applies an activation function like ReLU or leaky ReLU, whatever. And the network learns what combinations of input features are useful in the hidden layers. Okay. In other words, let me take a step back. The value of this h1 depends on x1 times w1 plus x2 times w2 plus x3 times w3. All of these added plus a bias. Similarly, h2 is same as x1 times w1, but in this case, this is a different weight. In fact, I should have said this x1 w11, x2 w1, w21, and so on. And this would be x1 w12, because the weight of x1 connected to h2 is different. This weight is different. Okay, so those are the weights that the network actually learns when we do the training. Once we know that weights, we know how the model, is, ready for future predictions. We'll get there, slowly get there. I know this is going to be a long video, but I'm not rushing intentionally to make sure every detail makes sense to especially the newcomers, to the field of deep learning. So these are hidden layers, and you can have multiple hidden layers and one output layer. For binary classification, a single neuron with a sigmoid activation outputs whatever that probability is. If you know that the probability of the image being a dog is 0.9, that by default means the probability of it being a cat is 0.1. That's what I meant to say, okay? Now, if you ask the question of how many neurons and how many layers do you need, like do I start with 128 initial and then 64 and then 32 and then like keep going, or like do you need a very shallow but a very broad one, like for example 2048 neurons in first layer and then 256 in the second layer and then done, right? So what is the right architecture? And it's a tough question to answer. You need to experiment with your data, start with 1 or 2 hidden layers. because very deep networks are rarely needed for at least our type of exercise. We just have a tabular data of feature vectors. And yeah, more neurons or layers give more capacity to learn, but again, there is a risk of overfitting. So let's go ahead and draw a clean MLP. Oh, I hope this is fast. Yeah. So this is not a slow operation. Again, I'm running these cells occasionally. We don't need GPU again to do any of these. So here you can see the multi-layer perceptron for our cat versus dog problem. And we have 67 handcrafted features. So the first layer, you have 67 of them, and then one output. All of those go through one hidden layer in this, two hidden layers actually, right? The green ones. So hidden layer 1, that actually has 64 neurons. The next one has 32 neurons. I'm not showing all of those. I'm just showing a handful of them. And then they're all connected to one output layer. Or you can actually have a smaller example. I'm just giving you a smaller example. You only have 4 inputs, and then you have 1, 2 hidden layers. In this case, 5, and in this case also 5, neurons. And then you have 3 outputs right there. It can be cat, dog, and I don't know, it can be a bear or something, or a tiger. So this is your output layer. Each one has a probability in this case. And we use a function called softmax for multi-class classification problems. And if it's a binary classification, a sigmoid would do the job. Again, if you remember earlier, we saw the sigmoid, the S type of curve, and it outputs between 0 to 1, right? And if the value is closer to 1, it's dog. If it's closer to 0, it's cat. It's worth repeating many times if you're learning it for the first time. Okay, now, you probably heard of the term, especially like ChatGPT version 1 has 4 billion parameters. Someone says the next version has 20 billion parameters. And then we are heading towards 1 trillion parameter models. What in the world are these parameters? What do we mean by parameters? Well, first let's see. The parameters are nothing but your weights and biases that we saw earlier. Remember, each neuron connected to another neuron, and then you multiply the value with a weight. So that is a parameter that the model needs to learn, because you start with something. Typically, you start with some random values that are drawn from a distribution, right? And then the more training happens, the more these weights get updated. And then at some point you say, okay, the training is good. And that's where the weights you actually take. And that's the trained model. A trained model is nothing but a model architecture plus the weights and biases that actually go at every point in that model architecture. Okay. So in our case, we have 67 inputs, right? 67, our feature vector is size 67, and they're connected to 64 neurons in the next layer. So each neuron has 67 weights, right? So each neuron must have a weight. So it has 67 weights plus 1 bias that gets added. So right there you have 68 parameters. So total in layer 1 is you have 64, because they're all connected to 64 different neurons in the second layer, multiplied by how many? 68 parameters. So you have 4,352 parameters that need to be learned in the first layer itself. Now go to layer 2. Now from first hidden layer, you have 64 neurons connected to 32 neurons. You do the math exactly the same way. 64 plus 1 bias, 65 parameters. 65 multiplied by 32, you have 2,080 neurons right there. And in the output layer, you have 32 inputs that are going to 1 neuron, right? So you have 32 weights plus 1 bias, 33 parameters. You add all of these, and that gives you the total number of neurons. That's basically it. So here is just a visualization or just a quick calculation of what I just mentioned. Okay, so so when you do this, you end up with the total of 6,465 trainable parameters, meaning that many parameters that we need to train and embed in our model. Now, if you basically train on raw pixels instead of extracting features, we went through all this exercise of generating features and creating a feature vector and now using the feature vector to train the model. Why do all of this? Why not just supply an image? Every pixel. Well, if you want to do that, then even a image of 128 by 128 raw pixels connected to 64 neurons, you get like 1 million parameters in just one layer alone. That's it. It's not practical. If you have large images, if you have many images that need to be, many layers, for example, that you're using as part of your network, it doesn't get, it's not practical basically. So handcrafted features dramatically reduce this parameter count. Okay, now that you understand how these neurons are connected and what these input values mean, what the weights are, and all of that stuff. Now the question is, how does the model actually learn? Okay, you supply an image. How do we get the right weights? Let's learn that in this part. So a learning process involves three key things that you probably heard: loss, gradients, and backpropagation. Loss function should not be new to you. Loss is basically, where is it? When we measure, I should have put an easy way. Loss is it's not just with neural networks. For example, when you do linear regression, what do? You have you're trying to minimize your mean squared error between your predicted and the actual values. And once it's trained, you have a nice linear regression formula. The mean squared error in that case is called the loss function. Anytime we refer to loss function, that's the function that we are trying to minimize by plugging in the predicted values and comparing them to actual values. And once we minimize the loss function, that's where we say that the problem is converging or converged. And this is basically in the optimization problems, loss function gets often used. And in our case, we use something called binary cross entropy as the loss function, because in our case, it's a binary problem. Yeah, even if it's a multi-class problem, you can still use binary cross entropy, except you just compare two things at a time. Now, you know that there are two things here: binary cross entropy. Yeah, so Y is the true label in this loss function. This is the true label, let's say cat or a dog. And P is the predicted probability. Let's say Y is equal to 1, which means it's a dog. Okay? And 0 is cat. And if the probability comes up to 0.9, then 1 multiplied by log of 0.9 plus 1 minus Y, which is the cat, in this case, because if Y equals to 1, 1 minus 1 is 0. And log of 1 minus P, which is nothing but the probability of that being a cat. It's nothing but probabilities adding, and then you have minus 1 right there. Yeah, that's basically the loss function. Not much to, I don't know why I'm explaining certain things in detail. Maybe some of you are getting bored, but I hope at least some of you are learning what's going on here. Okay, so now you understand loss function. And this is a simple loss function. There are many other loss functions. There are very complicated loss functions, especially when you get to convolutional neural networks and images. You can use something called Jacquard index, for example. Yeah, I'm not going to explain what those are, but loss functions can be anything that reflects the accuracy of the prediction or inaccuracy of the prediction, and you're trying to minimize that inaccuracy. That's all. That's a loss function. Now, gradient descent, the loss function, the loss is a function of all the weights in the network, right? So a loss function actually, in our case, we have 6,000 weights or so. And the loss function actually includes all those 6,000 different information from all 6,000 neurons. So if you plot them, for example, as a landscape, if you plot the loss function of all the neurons that we have, where each weight is a spatial dimension, meaning we are just placing them in this spatial dimension, how does the surface look like? This is, let's say, how the surface looks like. We are trying to minimize the loss function, which means you don't want to be at this high point. You want to find the deepest point right there, preferably the deepest of all, not a shallow deep. You don't want to end up right there. That looks like it's converging. You want to find the true global minimum. That's the actual solution of this problem as described by all these weights in your neural network. So if you actually adjust the weights correctly, and you're getting your dogs identified as dogs correctly 99.999% of the time, then you probably found this true global minimum in the loss function. I hope that makes sense. Now, what do I mean by gradient descent? Well, gradient descent is an algorithm that navigates this landscape first by doing two things: by computing the gradient of the loss with respect to every weight, and moving each weight a small step in the opposite direction. Now let me simplify this. A gradient descent is nothing but if you are blindfolded and you are like in a nice, well, not nice, but in a curvy, let's say on a hilly area, you're blindfolded and your goal is to find the minimum part of that hilly area. Well, obviously when you feel it, the surface with your feet, you're not going to climb up the hill because the goal is to find the bottom part. You feel it with your feet. Okay, this part of the land is going down. You take another step forward. You're like, okay, this is all still going down. Take another step forward, still going down. Oh no, it's not going down anymore. So you go the other way around and you take those steps until you find this minimum. That's exactly what gradient descent is. Yeah. And it feels whether the ground or this landscape is going down or going up. How does it feel? Well, what is a gradient? It's nothing but the differentiation of your whatever the curve is. And that's why you take a gradient, and if it's going down compared to the last one, okay, you're in the right direction. If it's not, then you're in the wrong direction. Adjust the weights and move forward. That's exactly what that is. Computing the gradient of the loss function, right? You have a loss function. In this case, this is the loss function. And you don't just compute, at one point, because you have 6,000 weights or millions of weights in parameters. So you compute this gradient with respect to every weight. If you have 3 million parameters, you compute this gradient for each and every weight. Okay? And then you update, moving each weight a small step in the opposite direction, right? Hey, it's going up. Let's go down then in the opposite direction. That's exactly what's happening right there. Now, learning rate is something like how big of a step do you want to take? Do you want to just take like tiny steps? Then you may not feel the gradient. Then it takes like almost infinity, to get to the solution. At the same time, you don't want to just take big jumps. Then you can't even tell whether the land is going, when it's going down or when it's going up. You want to find the right pace in terms of the learning rate. That's what that learning rate is. Okay. Now, another term called backpropagation, which you may have heard. So computing the gradient of the loss, which we just discussed in the previous step, with respect to every weight, right? It requires something called a chain rule of calculation. And backpropagation is the algorithm that applies the chain rule. Please go back and refresh your memory on calculus in terms of what chain rule is. And this gradient information is passed backwards through the network, and it goes through one layer at a time. You have your neural network, right? On the left-hand side, you have your features from the image. On the right-hand side, you have your final probability, your output. In between, you have these hidden layers. And a forward pass basically means you go from the features and all the way to, that's where you find out what the output is. A backward pass is nothing but it's a computation of gradients layer by layer, right to left. It says, okay, the output is 0.9. So it should be a cat. Uh-oh, that's wrong. The real value is 0.2. I mean, the real value is cat, not 0.2. It's a 0, right? It's a cat. But I'm getting 0.9. That's way off, right? Let's go back one layer, adjust the weights. Get back one layer, adjust the weights. How does it adjust the weights? It computes the gradients and it moves the gradients in the right direction where you're actually gaining or you're actually going downhill and not uphill on this landscape of loss function. I hope that kind of makes sense. So that's all. The backpropagation is exactly that. And now you also have another thing called term in deep learning that you'll hear quite often, stochastic gradient descent, and another optimization algorithm called ADAM. Now, we just talked about backpropagation. Instead of computing gradients over the entire data set, which would be extremely slow because you have millions and billions of that, SGD, stochastic gradient, stochastic, it's in the name, it estimates gradients using a small random mini batches. You usually use like 32 or 64 or 128 or 256 mini batch and estimates this. Okay, instead of computing gradients on the entire data set, that's what it does. So that's stochastic gradient. ADAM is kind of similar. It keeps a running average of past gradients and a running average of past squared gradients. This means each weight gets its own effective learning rate that adapts over time. Again, please, if you want, this is again not a deep tutorial into how this everything works. I just want to introduce the terms, what they are, and at a high level explain what these are. But if you are really getting excited, there are millions of videos on YouTube that talk about each of these, and please go ahead and check those out. Okay, so visualize the loss landscape and gradient descent, and this is again in just one dimension, I would say, instead of our 3D landscape. So let's say this is your loss function, and we need to find the minimum. Ideally, you would find this spot because that is lower than this spot, right? You want to find the true global minimum. Now, in my case, the gradient descent, again, our learning rate is 0.01, which means I'm taking tiny steps. So I go from here to the red dot, to the next red dot, to the next red dot, and so on. And then I found this minimum, and the step I'm taking, the learning rate 0.01, is not large enough for me to find the true global. I'm stuck in this local minimum, which is probably okay in this case. I may get some decent results, but if the step size is larger, I would have actually ended up at this one. Now, the question is, what is right? There are some strategies. People start with larger learning rates, and then once you get closer, you can use smaller learning rates. Okay, and this is nothing but how it converges, for every learning rate. Yeah, not much to discuss there. And let's move on to visualizing the binary cross entropy loss. And again, we talked about binary cross entropy, which is very straightforward to understand. So you have a probability for dog going from 0 to 1, and for cat going from 1 to 0, let's say, right there. So this is the plot let's look at for now, because that's easy to understand. And this is the cat, which is in reverse. So it's just mirror opposite right there. So the true label for the dog is 1, right? So that's the true label. When the loss is absolutely minimum all the way down to 0, that's when we get a probability of 1. And initially, when we start with the training, we start with a high value. And as we present more and more dog images and cat images, the model learns, and the loss function is minimized and minimized and minimized. And when it's actually absolutely minimized, then it doesn't go down anymore. It kind of gets saturated in real life. So this is your binary cross entropy loss visualization right there. That's it. Now, a visualization of backpropagation, again, we discussed this. What happens is you update the weights. First of all, you do a forward pass, right? A forward pass is nothing but you're just multiplying and doing the math. Input feature vectors, x1 times w1 plus b, and then go to the next layer, do the same math, and finally you get your output. And when you get your output, your predictions, you have some predicted value. And you're like, okay, I have my predicted value. I know what the actual value is. That's what training is. You should know what the actual is. The actual is 1 if it's a dog, 0 if it's a cat, in our example. Now you're like, okay, I need to update the weights. So what you do is you update the previous weight by a small amount. What is that small amount? Well, learning rate multiplied by whatever that gradient is. So that's what you're updating. And the gradient can be a positive value or a negative value. So this weight can go up or weight can go down, the value of that weight. You update the weights, and then you do backward pass. You compute again How do you do the backward pass? You do a partial differentiation of your loss function with respect to every weight that you have, and that's how you compute the backward pass, meaning how to update those weights. Okay, and then comes computing the loss. So compare predictions to the true labels, and then do a forward pass, and then this is how the chain rule actually is displayed in reverse right there. Okay, now you heard about all the terms that goes into what is a multi-layer perceptron, which is basically a neural network, and how it actually works. What is an activation function? What is stochastic gradient descent? Now let's actually bring all of that into one place. Now, when you build this network, there are a few terms that you should know. One is epoch. An epoch is nothing but when one complete pass through the entire training data set. You have 1,000 images for cats, 1,000 for dogs. When these 2,000 images go through the network once, it's called one epoch. Okay, and a batch is you cannot just fit all 2,000 images into the network at once. You actually send them in batches, and that's basically a batch, right? You say, okay, I want to feed 32 images at a time. So a subset of the training data used to compute one gradient estimate and one weight update. And dropout, okay. This is kind of important. Dropout, when you have like neural network where everything is connected to everything else, the model can actually be the term is overfitting, meaning it learns a lot about training data, especially if the network is deep, but not much about some new data. So it's not generalized enough. One way of adding this generalization, generalizability, or minimize this overfitting is via regularization and dropping. Dropout is one way of doing that regularization. Well, I used too many words. What this basically means is when you're connecting one network to the other network, when instead of every neuron connected to every other neuron, you drop some of those randomly. You drop some connections randomly. Okay, that helps in model not learning too much about the training data and keeping it generalizable. So that's what dropout is. And the way we define the MLP architecture, the multi-layer or neural network architecture, we are using Keras in TensorFlow. So let's go ahead and use the sequential method within Keras, and I'm giving it a name, MLP cat dog. And to that I'm adding, so I created a new model, blank model with nothing. Okay, to that blank model, I'm adding an input layer of whatever the input dimension shape. Okay, and then I'm adding a dense layer with how many neurons? Well, how many ever I have here, starting with 128 first. The next round, I'm doing a 64. Number of neurons, and then 32. That's what this block is doing. But it's not just a dense layer. Dense layer is nothing but your neurons, where it's basically a neurons. And then between every one of these, you can actually perform batch normalization to normalize all the output values coming from that specific neurons. And then you, of course, you need to have an activation function, right? Otherwise it becomes a linear model, and we use ReLU activation right there, and then I'm adding some sort of a dropout. And how much dropout rate? About 35% dropout rate. That's a bit aggressive, I should say. 20% is probably okay. That's the dropout rate. And once you create those hidden neurons, then at the end I'm going to add a final layer with only one neuron, which gives me the probability between 0 to 1. Well, it gives me probability between 0 to 1 because I'm adding an activation function called sigmoid, and sigmoid goes from 0 to 1. That's it. This is very simple to understand, actually. And I'm naming that layer as output. You don't need to name. The model gives default names anyway, but it helps if you actually add names. It makes the model more interpretable if you want to print them out. Once you do that, you compile the model using what? Using an Adam optimizer. We discussed what Adam is, well, kind of briefly. And what learning rate? Well, in our case, we're using 0.001. And what loss? We're using binary cross entropy. And what metrics to track? We are tracking accuracy as the metric. which makes sense. That's it. And now we built our model, and there you go. That's our model. Yeah. This is one way to visualize your model. Another way to visualize your model is like right here, where you can see everything connected to everything else. Okay, this tutorial is getting a bit long. I was aiming for 45 minutes, but I still hope some of you are watching this, and we are getting there actually. Now we are ready to train this multi-layer perceptron, or the neural network that we just created, but we are adding a couple of callbacks. Callbacks is a parameter that actually goes into your model fitting. And here we can define early stopping conditions. We'll say, okay, if the loss value is not improving for the next 20 epochs, go ahead and save that model and say this is the best one. So even though my number of epochs may be 200, the model may stop like after 40, 50. If it reaches, the point where it's not learning anymore. And the reduce LR on plateau, reduced learning rate on plateau. Basically, it's once the learning rate actually senses the plateau, around that plateau area, it just reduces the learning rate by a factor of whatever the factor you define over there. That's it. And then it's nothing but model.fit, your training data, and then number of epochs, your batch size, and what callbacks are we using, and that's it. And this is the output. You see the initial learning rate 0.3005 and then 0.3025. It kind of reduced the learning rate right there. But more importantly, this is exactly what we ended up with, 62.8%. You may be wondering, we did all this for this. We got the same accuracy using random forest. Why didn't we get any better? People tell me deep learning is amazing. It gives me great results. Yeah, it's great, but it depends on your input data. In our case, I should say we are limited by the type of features that we actually generated. The features that we actually engineered, they are not representing any differences between the cats and dogs. And we did pick a pretty difficult example. Yeah, if you have a whole bunch of, let's say, black dogs versus white dogs, that's an easy problem. But cats versus dogs, the animals look the same, the background looks the same, animal looks the same for the computer. Like we're not using the full feature set. Well, cats have pointy ears, but our features don't capture that information. That's exactly why we need convolutional neural networks. In the next tutorial, we'll discuss that, how to improve, and hopefully with CNNs, we get much better accuracy than 62%. We'll see that, so please stay tuned for that tutorial. Now, let's also look at the training curves. Typically, the training curve should obviously start at the high value. This is the loss, by the way, on the y-axis, binary cross entropy loss. And the loss should go down and down and down and down all the way to, this value depends on what exact loss function you use. So the exact value is not that important. What's important is it going down? Is the loss? And then is it saturating? Once it's saturated, that means the model is not learning. It reached its peak capacity of learning. Other thing that's important is this blue line, which is the loss for the validation data, which is our test data, right? We split our data into training and testing. The training curve is this red one. And the testing, which this data never got into the training model. So this difference tells us the model is overfitting. It's learning about the images, the training images, a lot. So it can probably give you very good discriminative power for the images that were used as part of training, but not for the testing ones. That's not good. Okay. But of course, this is a very shallow model, not many neurons, and handcrafted features are bad. So that's the reason. And let's also look at the confusion matrix. 62% correctly classified as a cat, 63% correctly as dog, all the other ones are wrong. And we looked at this in the last tutorial, ROC curve. So this is the curve, and the area under this is 69.4%, let's say. So the random is 50%. Now we are getting 69. That's okay. That's not bad, but it's not good for sure. Okay, so understanding what the network, again, I'll skip through these. You can read through them. There is not much to, I mean, there is a lot to learn, but not much to learn right now from our data because everything looks pretty random. So there is not much. Here, I'm asking the question of, can we identify like different features, the weight matrix for the first hidden layer? So for each of our neurons in the first hidden layer, we have 128 neurons in our first hidden layer. If you remember, for each of those, if you look horizontally here, input feature index, is there any trend that we actually find? Is there like everything that's red or everything that's blue? To me, I don't see much of anything. That's why I'm trying to skip this through. Again, run this code with your own other data, not just cats versus dogs. Then you may see some trends over there. Here, which features does each neuron in layer 1 respond to most? And again, not so useful in our case, but if you want, you can just go ahead and check this. Again, we have all of these Gaussian mean and the quadrant mean, and we have a whole bunch of input features that we just generated, right? And which features are showing in the positive weights, which are in the negative weights, like the largest weight. But again, this doesn't tell us much about anything, at least at this point. And but I'm giving you code so you can plot this on other data. Inspect neuron activations. Like in this case, we are asking the question, do activations actually help in discriminating cat versus dog? And again, I don't see, if there is a good separation between this red and blue, I would say yes, if they're separated, but I don't see much any difference between mean activation in both type of plots. The right type plot is what I normally use, and I don't see much of anything right there, right? So now predictions, correct versus incorrect samples. Again, there are various ways of looking at your results and trying to infer something from the results. And I'm just showing you a few of those, and hopefully you'll find them to be useful. Now, this is something that's useful on the left-hand side, right? So the confidence correct versus incorrect samples. On average, you see the correct samples, you have the distribution to the right. Incorrect, you have the distribution probably slightly to the left, but not enough. One thing to confirm here is, mean confidence of correct predictions is 0.343, of the wrong predictions is 0.241. You don't want a model to be confidently misclassifying something. And this is where I usually check that. I hope that makes sense. You don't want the model to say, oh, I'm 90% confident that this is a cat, but in reality, that's the image of a dog. That's when you have a crappy model, obviously. You don't want that. If it's getting things wrong, it needs to be, it better be uncertain about it. Yeah, that's what we are looking at here. And now let's look at the effect of architecture choices. We talked about this earlier. What is the right architecture? It's tough to answer that question. So you can actually do parameter sweep. Like for example, in this case, I'm showing you a shallow configuration, deep, narrow, 64 by 32 by 16. In this case, there is only one layer of 64 hidden neurons. There is another hidden layer of 256. Like so, your input, hidden layer with 256 neurons, and output. That's it. And here you have 64, 32, 16, and a few other combinations. And this is exactly what we are looking at. For each of these, what is the accuracy? Let's ignore the train accuracy, only look at the test accuracy. Okay, 67% and 62% and 64% accuracy. Now, if you actually look at the number of parameters, for example, the one with 18,000 parameters, which is very shallow, 256 neurons, you see the training accuracy is almost like 79% right there. But then the test accuracy is only 62%. That's classic overfitting. Okay, so this is just the architecture, and visualize the architecture comparison. Again, we are pretty much the same output, plotting it. Some people like plots. I like numbers more than plots, but in some cases I like plots. Now, effect of dropout rate. In our model, we actually included a dropout of 35%, if I'm not wrong, 0.35. Now let's see dropout of 0, 0.1, 0.2, 0.3, 0.5, and 0.7 and see how it affects our output. And you can see the dropout rate, as the dropout rate increases, the accuracy is actually compromised. Yeah, well, you're compromising on accuracy. The accuracy goes down, but at the same time, the overfitting actually minimized. Here you see the accuracy difference between the training and the testing data, humongous. That means the model is overfitting. And that gap actually narrows as the dropout rate increases. But we don't want to increase it to the point. Did I put... yeah, obviously from the plot you can see the accuracy actually goes down to about random, like 50%. When the dropout rate is 0.7. That means the model is not learning anything. This is probably not a bad spot. You're getting decent accuracy of about 67%-ish or so. And the dropout rate is 0.5, and the model, the difference between training and testing is not that much. So this is fine. So this is what I would actually pick. I hope you're still learning something from these. And before ending this video, let's go ahead and look at how our previous tutorial like random forest and this MLP, in both cases we use the same features, by the way, exactly the same features. And we are comparing both models, trying to see if there is any advantage of using MLP versus random forest and vice versa. Let's go ahead and look at the result directly. They both look exactly the same. That's the answer. Random forest actually gave us a accuracy of 63.7%. MLP gave us 62.8%. They both are statistically, to me, identical. And yeah, you don't see much of an advantage. That's why I say we are limited. If you plan on using random forest or MLP with your own engineered features, you better find better features. Yeah, that's the lesson we learned right here. At the same time, I hope you learned a lot about MLPs and different parts of neural networks. Okay, this is just one training. Let's actually do training on our cross-validation, like with 5 splits. We are splitting our training data into 5 different splits, our data into 5 different splits, and presenting different training data each time. So that gives us a true indication in terms of how the model is learning. And you can see the random forest, on average, it's pretty high compared to MLP. So random forest is doing much better. Well, not much better, definitely better than MLP. And if you want to look at the values, random forest gives us 62.4% versus 59.8% for MLP. In both cases, they're above 50%. So they're learning something. So better than random. We can predict if it's a cat or a dog. Definitely better than random, but not much better than random. Only 10% above random. That's it. And hopefully we can increase that, improve on this when we get to the next tutorial, which is the last tutorial as part of this series, at least the series that I am planning. This is about convolutional neural networks. We'll also do transfer learning and use a architecture called VGG16. All of that will make sense in the next tutorial, so please come back. And this is probably longer than an hour, and I really appreciate your patience, which tells me that you have learned something, and I assume you have watched the entire tutorial. Thank you very much. Let's meet again in the next tutorial. Bye.